All right, you guys, we're going to continue our discussion on logarithmic functions. So on this slide, you can see that we are going to try to determine the domain and range of any logarithmic function. So it says the logarithmic function y equals log base a of x has been defined as the inverse of the exponential function y equals a to the x. That is, if f of x equals a to the x, then the inverse function equals log base a of x. So we discovered that based on our talk about inverse functions. Okay, so what we know about inverse functions is that the domain of the inverse is the exact same set as the range of the function. And we also know that the range of the inverse is the same as the domain of the function. Inverses and their functions will always share that relationship. Okay, so what we do know is that the domain of the log function is the exact same thing as the exponential, the range of the exponential function, which is 0 to positive infinity. Okay, what we also know is that the range of the logarithmic function is the exact same thing as the domain of the exponential function, which is from negative infinity to positive infinity. Okay, so the important thing that we're going to be looking at is if we are asked to find the domain of the log function, that it needs to be from 0 to positive infinity, which is all positive numbers. Okay, so let's look at some examples. All right, so it says to find the domain of each logarithmic function. And so we have A, B, and C. So let's take them one at a time. So let's look at A. So A is f of x equals log base 2 of x plus 3. Okay, so for a logarithmic function, okay, the domain is 0 to positive infinity. Okay, which means whatever values you plug into the argument of the function has to be positive. Okay, so the argument of this function is x plus 3. Okay, so whatever we plug in there has to keep that argument positive. So what we want to do, we want to set up this inequality. We want to say, well, x plus 3 has to be greater than 0. Okay, and we're going to solve that. So we're going to subtract 3 from both sides. And we have x is greater than negative 3. So this tells me that I can plug anything that I want into this log function as long as the x value I plug in is greater than negative 3. Okay, so if you're asked to find the domain, remember you can write domain using two different notations. If they ask you to write it in set builder notation, you'll write brace x such that x is greater than negative 3. If they ask you to write it in interval notation, that's going to be parentheses, negative 3 to positive infinity, parentheses. Okay, so for the interval notation, remember we're using parentheses because we don't want to include that negative 3. Okay, all right, let's try B. Okay, so B says g of x equals log base 5 of 1 plus x over 1 minus x. So once again, our domain of our log function has to be positive. Okay, so we want to set this argument 1 plus x over 1 minus x greater than 0 because we want to ensure that it stays positive. All right, so in this argument sits a rational. Okay, so if it helps you, you can kind of label what was sitting in our original arguments. So in the argument of A, that was a polynomial function. Okay, what's sitting in the argument of this log function? This is a rational. So I know it's a rational. It looks like a fraction. Okay, so whatever we plug into this function cannot equal 0 for this rational, or it's going to be undefined, and it's got to be greater than 0. So we're going to set both the numerator and the denominator equal to 0 to find out what those values of x are. So we want to find out what will make the numerator 0. So we have 1 plus x equals 0. And we also want to find out what's going to make the denominator 0. And we're going to solve these. Okay, so if we plug in negative 1 into the numerator, it's going to create a 0. And if we plug in 1 into the denominator, it's going to create something that's going to be undefined. So because this is a rational, okay, there's going to be intervals of where this is either going to be positive or negative. So I'm going to draw a number line to help me figure out where those intervals are going to be. So my two values for x that I got, I'm going to place them on the number line the way that they would naturally occur. So -1 is smaller, and then 1. And when I put those on the number line, they create 3 intervals. The first interval is from -infinity to -1, then -1 to 1, and then 1 to positive infinity. And then I'm going to choose test points because I'm interested in the values that are going to make this interval positive because the domain cannot be negative, okay? So in this interval, let's say I choose -2. And remember, for test points, you can choose whatever you want as long as that value actually falls in the interval. Okay, so those are my test points. And I'm going to plug them into this inequality to see if it makes it true or false. So I have 1 plus -2, 1 minus -2. If you subtract a negative, it becomes positive. It's 3. So is -1/3 greater than 0? No, this is false. So we don't like this first interval. All right, I'm going to try the second one. Is 1 greater than 0? Yes, that's true. So we like that interval. And then we're going to try the last one. Is -3 greater than 0? No, that's false. So we don't like the last interval. So if we're looking for the domain, we can choose any value we want between -1 and 1. That will give us a domain, values that were going to be positive, okay? So the domain for B, let's change the color. All right, this domain, okay, if we wrote it in set builder notation, okay, would be all x such that x falls in between -1 and 1. And if they asked us to write it in interval notation, it would be parentheses -1 to 1, close parentheses, okay? So that's what happens if our argument is a rational function, okay? So if you're looking for these domains for these log functions, remember that they always have to be positive. But the way that you set them up, you're always going to create inequalities that are greater than 0. So for our first one, for A, the polynomial function, it was a simple linear problem. We just solved the linear inequality. For a rational, you had to keep in mind that you're looking for values that make the numerator 0 as well as the denominator. And then we have our last problem here, which is C. So we have h of x equals log base 1/2 of the absolute value of x, okay? So for a log function, whatever sits in its argument has to be positive, okay? Now, what sits in this argument is an absolute value function, okay? So we know an absolute value, okay, it's never going to be negative. Anytime you plug in a value into an absolute value, it's always going to make it positive. So the only value here that's going to give us an issue is 0 because the domain for a log function has to be positive, but it also can't equal 0. So x for us cannot equal 0. So if we write that in set builder notation, it would be all x such that x does not equal 0. If we wrote it in interval notation, we would say -infinity to 0, parentheses, union, 0 to positive infinity, okay? So when you're solving for the domains of these log functions, not only do you have to keep in mind that the domain of a log function has to be positive, you also have to take into consideration what kind of function sits in its argument, okay? So is it polynomial? Is it rational? Is it absolute? And to take those considerations in as well, okay? Cool.